All right, and welcome back, everybody. So we are well on our way to understanding how to solve differential equations, and we're really starting to pick up steam in learning what certain methods are available to us, especially in first order. But what I wanted to do here is take a bit of a detour and to remind us why we're looking at differential equations in the first place, and maybe see a little bit more about how we develop mathematical models. And we did this a little bit in a previous video, talking about the free fall model that we created. And what we actually want to do here is give a general framework for how these kinds of models come about. And there is a bit of a process, there is a cycle, and it's all rooted in the scientific method. So what we have here is an observation, right? We see some sort of physical phenomenon. And so this could be anything from a falling object slowing down due to drag, or maybe it's some chemical reaction going to equilibrium. Maybe it's a population of, let's see, a population of animals that you want to study. Physical examples and phenomena. Usually that's where you pick up your observations. And what you wind up doing in the scientific method here is you wind up asking a question about this observation. It's like, does it always do this, or is there something else that you're curious about? So you create, from your observations, you formulate a question, and that question leads to a hypothesis, right? And you say, sure, this always happens, and we can try to test it. Or maybe there's going to be a maximum population size. Something interesting is occurring in your system. So this hypothesis leads to the construction of a model. And this is what we are doing in the notes on the left-hand side. This is effectively where the differential equation comes into play. Construct a mathematical model. And this is going to be the case, or this is going to be the box in this diagram that we care about the most. So we begin with a question, so I'll put that guy in red. So this is effectively where we begin this process, that there is a question involved. And we formulate a hypothesis that tries to answer that question, and then we use a mathematical model to try to answer that question. Now, we build the mathematical model here, and this is usually some differential equation, maybe not even an ODE, but usually just some differential equation that comes into play here. Now, next, we need to analyze the model, right? So whatever this means, this could be solve the differential equation, or study some sort of numerics associated with it, or look at some geometry associated with the equation, but there is going to be some analysis that you have to make. And more often than not in our series here, this usually just means solve the ODE. Right? And once we analyze that model and figure out here's a solution, we start to figure out what makes a good approximation to our physical phenomenon. So we ask ourselves, did we get at an answer, or did we, or we should compare. Sorry, we should compare our solution. There we go, against data. So usually there's going to be some physical experiment or simulation that you can run that will compare your solution against, or compare against your solution. And your solution is supposed to reasonably predict or approximate this data. So usually there's some sort of statistical analysis that goes in at this step. So yes, technically that is an analysis, and that should be up in this previous step, but no. What we're doing in the previous step is analyzing the model itself, and that usually just means solving the differential equation, or finding different aspects that arise from it, or different features that are noteworthy within that model. Once you have your model and you understand it very well, you're going to compare that against your data. And we ask the all important question, the ever important question: are we happy with the comparison, or with the comparison? So does this equation actually model our scenario well? And if not, then we're going to go ahead and start this cycle all over again, right? If we don't like the comparison, maybe there's some aspect that of this system, this physical phenomenon, that we didn't incorporate, but maybe it's up here in our observations. Maybe we did observe that there's something that we should add to or try to incorporate into this model. So either no, we're not happy and we start changing the model and iterate this guy all over again, or if we are happy, then we actually get to answer the question. And we're done. And this whole process here, this beginning, and I don't want to box that in white, I want to box that in red, so you can say, or green. Let's do green, because we started with red, and red is like, hey, stop, go ahead and iterate this cycle, and then when we're happy enough, we go ahead and say that green, we have an answer to the question. So this process is the modeling cycle. Right? And it's a very heuristic diagram, just designed to tell you about all the different aspects that go into this model. And there are a few things that we should really talk about within this model, or within this cycle. But as far as this class goes, we are really paying attention to these two bubbles on the right, or these two boxes, where we need to know how to construct a model, and we need to know how to solve it and analyze it once we have it. But a couple of things that we should note about constructing a model, and I want to make this abundantly clear. Nature does not follow our mathematics. And I want to make this abundantly clear. Right? It's oftentimes misconstrued that nature, or that a mathematical model, like some differential equation or some function that's describing some physical phenomenon, is the end all be all law that the universe must satisfy. And no, actually, that is definitely not the case, right? Our mathematical models are here to approximate some physical phenomenon. They are proposed mechanisms by which something occurs. Right? So the math supports nature, but nature does not have to follow the mathematics at all. Right? Our job is to propose a mechanism by which something works. Right? And for a lot of differential equations theory, and a lot of STEM fields in general, like physics and chemistry and biology, what we're doing in general is trying to come up with a way to describe something so that we can predict how it will behave under a certain change in conditions. And that could be a class unto itself. Like, there are often classes in mathematical modeling, or seminars or contests just in mathematical modeling. It is a very subtle art more than a science in some cases. So what I'd like to end on here is to just remind you that math is an important tool for being able to study physical processes, but the physical processes, the natural phenomenon that we observe, are not working off of some equation. They don't plug in numbers to an equation and then figure out how to operate from there. No, the math is here for us, and it's an abstraction for us to understand the physical phenomenon. And we'll walk through this process, this entire, maybe not the entire mathematical model, but at the very least, the first two steps of trying to construct a model and analyze it by solving a differential equation. And a little bit at the end here, we'll talk about whether or not that model makes any sense against intuition more than empirical data.